Anyone else looking for this today? Any of you on the issues? Olivia?
Yeah.
Samantha? Julian? Here. Claire? Allison? Lauren? No. Really?
Yeah.
Nicole?
Here.
Cassandra?
Yes.
Anna? Christina?
Here.
Breakfast?
Here.
Alexandria? Annabelle?
Here.
Ryan?
Here.
Juliana? Laura?
Here.
So today, I want to get as far, at least, as what I asked you guys to read, and hopefully farther. The message going forward from here to the end of chapter 5 is, even if the theory doesn't make sense, even if particle wave duality isn't something that you can wrap your head around. The fact is, it works. Maybe at some point in the future, we will discover something that, or find a way of thinking about this that confirms Einstein's idea that matter at its most basic level is not governed by the laws of probability. But so far we haven't. So since about 1927, this is pretty much it. Okay. And the notion that electrons are particles that follow a path is no longer part of any modern atomic theory. And although it's taught in grade 8 and 9 and 10, at the very least, I think what bears reminding to students is that it's not the way it really is. And it's simple. It's analogous to see the electrons as like planets orbiting the sun, but they don't do that. They don't follow a path. They don't behave like particles. So the probabilities that we're going to talk about today are really identifying, based on the energy we give every electron, where is the most likely, or what is the shape of the most likely probability volume for any electrons with that energy. And we're going to start with hydrogen, and we're going to go right up to the 4th energy level. And every time we get to a new energy level, we're going to find that there's a new shape of the probability volume. And the names we give these shapes all stem from wave mechanics, okay? And I'll tell you what I expect you to know, and I'll tell you what it's not really important to know, but it's from here on in, it's pretty simple, as long as you can wrap your head around the fact that, okay, tough to understand, but it works. So all we're really doing is applying what we know is the best we can do. What part of Bohr's theory remains as part of the quantum mechanics of the atom? So remember those three most important aspects or constituents of the will, the quantum mechanical view of the atom. What's the first part of the first sentence in the first one? Remember I said I will promise that that will be the test question. This is the end of section 5 through. When I went through it on the board, I said, this is Bohr. Yep. Quantum. The energies of electrons and atoms are quantized. The energies of electrons independently of nothing else aren't quantized, but in an atom, they are. Okay? He didn't know why, but that begins really the first of those consequences. The energies of electrons and atoms are quantized. And we're going to begin with that as we identify these probabilities of it. Okay, let's give an electron, a hydrogen electron, anything we want. See what Schrodinger's equation spits up. Then n equals 2, then n equals 3, then n equals 4. Quantum mechanics replaces the concept of an electron orbit with an orbit. This is the third of those consequences. Those regions in three-dimensional space around a nucleus where electrons with a particular energy are most likely found. The laws of probability are a necessary part of describing electron behavior. Why? That's the second one, the Heisenberg uncertainty principle. But all three of these things are the things we're going to have to employ as we effectively calculate elements with the electrons and where those electrons most probably are. In this section, we'll apply the quantum mechanical model we have to describing electrons in the atoms and the elements. We'll begin with hydrogen and then use that information to expand our discussion to include multi-electron atoms. And remember, the Bohr model didn't work at all for multi-electron. In the previous section, the analogy of a guitar string helps inform the requirement of standing waves in allowed energy states. Indeed, that's basically how de Broglie's hypothesis explains quantized energies. And that's the second part of that first sentence in consequence number one. The energy of electron is atoms are quantized. Energies of electrons and atoms are quantized because of their weight, which means the only allowed energy states are those in which we can maintain a standing electron. If you don't see the electron as a wave, you can't explain quantized energy states. If we solve Schrodinger's wave equation for the allowed energy states for hydrogen, we see that each energy state results in different numbers and types of orbitals. The equation shows us that the higher the energy, the greater number and types of orbitals present, the greater number and types of probability volumes. So in the first energy level, there's only one probability volume, there's only one shape. When we take that electron and excite it to the second energy level, there's two shapes, two probability volumes. Chemists usually refer to them as sublevels. When we go to n equals 3, there's 3 of them. And when we go to n equals 4, there's 4 of them. How many blocks are in the periodic table on the back of the book? That's one. Okay. And as it turns out, we only need those 4 shapes, those 4 probability volumes, to accommodate every element of the periodic table. Okay. In an atom, these 3-dimensional electron waves or orbitals are much more complicated than the standing wave in the guitar string. Remember, when we take that string and bend it into a circle, that's 2 dimensions. But we need a 3-dimensional volume, so it's a lot harder to wrap your head around what actually looks like. To describe them, quantum mechanics employs the use of special numbers called quantum numbers. Each quantum number specifies something different about the orbitals and the electrons in them. We will discuss these numbers as we investigate the orbitals associated with each of the allowed energy states for hydrogen. So the first of those, what turns out to be 4 quantum numbers, describing orbitals and electrons in them in atoms, is called the principal quantum number. And I'm not that concerned that you remember the name as the principal quantum number, but what it tells us is important. It tells us the relative size of the atomic orbital, the size of the probability volume. Okay? We have already been introduced to this number because it really represents the allowed energy states for the electron. Remember, the further away the electron is from the nucleus, the greater its potential energy. So the bigger the principal quantum number is, the larger the charge cloud we're looking at, okay? We know that the value of n can be a positive integer, 1, 2, 3, and so on. Again, courtesy of Bohr. When hydrogen's electron is in the lowest allowed energy state, n equals 1. And remember, Bohr called that the ground state or ground stationary state. I don't know if it's even like So when hydrogen electrons in the lowest allowed energy state or ground state, then n equals 1. So if we give hydrogen that amount of energy, Schrodinger's equation tells us with that amount of energy in 3 dimensions around that nucleus, it identifies points where the amplitude of the electron wave is the greatest, which is the same as saying a high probability of it being there, okay? Wherever the electron wave is the most intense, that's a probable location for the electron. If we connect all those points of high electron wave amplitude to each other, or enclose them in a 3-dimensional shape, then we see a probability density diagram. The cloud is what you might see if you could take many snapshots of the hydrogen electron around the nucleus and then superimpose all of them into one picture. Remember the video where the guy said one night Heisenberg took a walk. There's a famous park, and it came to him in a flash. That's not going to happen. What's the story about his park? Well, he used it to help explain the Heisenberg uncertainty principle. And he saw a beehive in this park, but it wasn't on the isolated island in the North Sea. It was just, he was walking in the park across from the Institute. And he says, you can't tell where any bee is going to be around a hive at any one time. But if you take a whole bunch of pictures of that beehive, you're going to see where they're most often going to spend most of their time. And that was the idea. Same with the electron. So if we took like jillions of pictures, if we could actually take a picture of an electron. For hydrogen's one electron, obviously in any instant, it's only going to be one place. And then you say, wait a minute, it's a particle in a wave. Indeed. But if you superimpose all of those pictures, so all the places in 3-dimensional space where an electron with that energy is mostly likely going to be is enclosed in a 3-dimensional shape. Okay? And what that looks like for n equals 1 is kind of a spherical cloud. At the center of the cloud is hydrogen's nucleus. So if that's the nucleus, if we take a picture of the probability volume of where the electrons are going to spend most of their time with that energy, and we wrap it in a 3-dimensional shape, from the outside, it looks like a sphere. Okay? But it's not equal density throughout. Remember, we talked about the fact that Bohr calculated the radius of that orbit in the ground state, called the Bohr radius. Let's say that we draw a graph with the origin at the nucleus. And what we have here is the probability of finding an cloud is an equal density throughout. If we give the electron n equals 1 amount of energy, what we get in terms of a probability is something like that. So where it's going to spend most of its time is a particular distance from the nucleus. So this is called radial probability. As you move out from the nucleus, there comes a point with an electron at that energy that it's going to spend most of its time. It could be here, it could be here, but it's going to spend most of its time about here. And that probability volume, so I say here, as we move out from the nucleus, we find that hydrogen's electron in its ground state is likely to spend most of its time a slight distance from the nucleus, rather than at the nucleus itself, which makes sense because there's a specified amount of energy. And the energy is because we're pulling that electron away from the nucleus. This is called the radial probability. It's interesting to note that the electron's distance from the nucleus to the region of highest probability, this distance corresponds exactly to the radius that Bohr calculated. Corresponds exactly to the radius of the orbit for the electron that Bohr calculated. Remember, however, that Bohr assumed that the electron followed a circular path and would always be that distance from the nucleus. Quantum mechanics describes this as the most probable result. So, according to Bohr, that was the radius of the orbit. The electron could be found that distance from the nucleus 100% of the time. quantum mechanics, no, that's just where it's going to spend most of the stuff. Okay? Now that's just in 2 dimensions. If we wrap that in a 3-dimensional cloud, from the outside, we see this. So this would be what we might see if we superimposed all of the pictures of where an electron at any instant is located with that energy. When we enclose the cloud in a volume representing about a 90% probability of finding an electron, we name that shape. We call it a 1s orbital. 1 tells us how big it is. The number 1 represents the principal quantum number, tells us the size of the orbit. And the letter S refers to the shape or type or sublevel, same thing. Now, you don't need to know what the letter S stands for. A lot of students think it stands for spherical. It doesn't. In wave mechanics, it actually stands for sharp. But you don't need to know that. Just call it S, okay? So if you look at the 2 diagrams here, figure 541A shows an artistic representation of what a spherical 1s orbital might look like if viewed from the outside. But let's say we splice that sphere down the middle, like cutting an orange, and you're looking at the side of it. So if we slice this thing right, and then we turn it and look at it, we're going to see something like this. And this is the radial probability, where there's the most collection of dots is this. Okay? So as we move out from the nucleus, not a lot of dots near the center, so low probability, but that would be the region of highest probability. Okay? So it's not the same density throughout. Figure 541b is a cross-sectional view showing the radial probability indicated by greater dot density, a slight distance from the nucleus. Now, in the first energy level, that's all we see. That's the only probability volume that exists. And we call it the 1s. S is the shape, 1 is how big it is, okay? Second quantum number. Now, you don't need to know that it's called the angular momentum quantum number. You guys talk about momentum in physics? So you probably have to talk about angular momentum, okay? You don't need to know this name, just know that it's the second one. What does it tell us? It tells us the shape of the orbit. So when we say 1s, there's actually 2 quantum numbers we're specifying there. There's the size, there's the shape. That's the type of orbit, okay? The different values of L are usually designated with the lowercase l. At each energy level represent the number of orbital shapes or sublevels. And as it turns out, they equal the number of the energy level itself. So for example, in the first energy level, we have 1 shape. It's an S. And because of its size, in the first energy level, we call it 1s. When we get to the second energy level, we still have the S, it's just bigger. So we don't call it a 1s, we call it a 2s. But in the second energy level, we have 2 shapes. So for n equals 1, there's only 1 shape, namely the S orbital. And shape is the same as sublevel, okay? Each new energy level has 1 new orbital shape in addition to those existing in the previous one. So if hydrogen's electron is excited, remember, anything that is in a ground state is an excited state. So if hydrogen's electron absorbs enough energy to go to the second energy level, which is bigger, then n now equals 2, not 1. And because it equals 2, as it turns out, there's 2 shapes, 2 sublevels, 2 types of orbitals. In n equals 2, there are 2 orbital shapes. There is an s orbital, same shape, just bigger, because we're further from the nucleus. So it's still a spherical cloud from the outside, it's just larger. So in the second energy level, obviously, the size of the cloud is going to be bigger. So we might get something like this. With that amount of energy, we might get something like that, where the electron is going to spend more of its time further away from you. It's still a sphere, it's just bigger, okay? Call it a 2s. 2 tells us how big it is, s tells us its shape. This means that the electron with this greater amount of energy will spend more of its time further from the nucleus. But there's also a new shape, and we call it a p orbital. As n equals 2, we call it a 2p. We don't see p orbitals in the first energy level. We don't see them until we get to the second energy. And it's kind of an interesting shape. It's not a sphere. It kind of resembles a dumbbell, sort of pinched in the middle. So if we can make sense out of this. So there's our nucleus, there's the 1s, there's the 2s, same shape. But we have what we call the 2p. So the outer boundaries of the p are the same as the outer boundaries of the s, the 2s, okay? And let's just get rid of that for a second. So this would be a spherical 2s. But we have a 2p that looks like this. Now, a sphere can't point in any direction in. But in the p organism, there is a direction. So you might remember this that we talked about earlier. Let's do a three-dimensional Cartesian set of axes. So we can call that the y if you want, and that the x if you want. Doesn't really matter. But then the one coming out of the board makes it three-dimensional. Okay. One of the 2p orbitals, and there are 3 of them, is right on the x-axis. Okay. We call it a 2p x. Okay. 2, that's how big it is. It's outer boundary. Piece of shape. X is another coordinate we're going to introduce soon. We call that the orientation in space. We'll talk about that soon. But we also have a p orbital orthogonal to that, 90 degrees. Right here. Okay. And that's called a 2p. If we're going to identify this into y and z, we could call that the 2y. Okay. Now we could call that x and y and z, or we could call that x, y, and z. It doesn't matter. As long as they're right angles to each other, what we label them is irrelevant. But the 2py, same size, same shape, just at right angles to the 2px. And then coming out of the board is a 2pz. So I said here, there is also a new shape, a p orbital. As n equals 2, we call it a 2p, and it resembles a dumbbell or long balloon pinched in the middle, where the nucleus is located. And notice, right at the nucleus, a p orbital disappeared. In other words, that tells us that in a p orbital, there's 0 chance of finding the electron right near the nucleus. You guys remember what I said, what we call a wave that has 0 amplitude? Remember what that term is? Node, N-O-D-E. That's going to come up in a few minutes. So the third quantum number then is something we have to pay attention to as soon as we identify the p's. And this doesn't tell us the size or the shape. It tells us the orientation in space of the orbit. The third quantum number, called the magnetic quantum number, and again, you don't need to remember that, but what it tells us, you do need to remember. It tells us the orientation in space of a given orbit. Now, with an s orbital, a sphere can't point in any direction. But with a p orbital, it can. So 2px, 2py, 2pz. Question? Right. The number of possible different orientations in space for any orbital shape represents the number of individual orbitals. So there's 3 different p orbitals because they can face in 3 different directions. There's only one s orbital because a sphere can't have a direction. So in the first energy level, all we have is an s. But in the second energy level, we have 4 orbitals. We have the 2s, we have the 2px, we have the 2py, and we have the 2pz. And as it turns out, the number of energy level tells us the number of different shapes. But the square of the energy level tells us we need orbitals. So in n equals 2, we got 4 orbitals. 2s, 2px, 2py, 2pz. But we only have 2 shapes, s and p. Make sense? Only a single s orbital exists in any given energy level because a spherical cloud can have only one orientation in 3D space. However, this new p sublevel, or p orbital, or subshape, includes 3 separate orbitals, each with a different spatial orientation. If we consider a 3D set of Cartesian coordinates, one is oriented along the imaginary x-axis, another imaginary y, and another imaginary z. The other 2 orbitals are oriented along the x and z axis and called appropriately 2px, 2pz, 2py, 2pz. Each of these 2 p orbitals is identical in energy to the other. For hydrogen, and only for hydrogen as it turns out, they're also identical in energy to the 2s. Chemists call orbitals of equal energy degenerate. Isn't what that word means in everyday speak, but to a chemist, a degenerate orbital is equal in energy. So for hydrogen's 1 electron, when we take that electron and put it in the second energy level, the 2s is equal in energy to the 2px, the 2py, and the 2pz, which means in a probability discussion, the likelihood of the electron being in any one of those is identical, right? But that's only for hydrogen, as we'll see. And here's some diagrams of the p orbitals. In figure 5.4.2, note that the lobes of each p orbital in the first 3 diagrams disappear at the origin. This means that the amplitude of the electron wave at the nucleus in a p orbital is 0. Which means in a p orbital, there is 0 chance of finding the electron right near the nucleus. And here we just have them superimpose everything. Okay. Now in this diagram, z is this way, y is this way, x is this way. But again, it doesn't really matter what we call it or z. We noted earlier that the number of different sublevels or types of orbitals or shapes in any energy level equals the value of n. So when n equals 2, we have 2 shapes. We also see here that a total of 4 orbitals exists in the second energy level. So whereas the value n tells us how many shapes there are, in addition to the energy level, n squared tells us the number of orbitals. In this case, 2 squared is 4. Why are there 4? Because we've got 1 2s and we've got 3 2p's. These 3 quantum numbers, the principal quantum number, the angular momentum quantum number, and the magnetic quantum number, first, second, and third, specify any orbital in any atom. It tells us the size, the shape, and which way it's facing. Okay? And you might say, well, wait a minute, you said there were 4 quantum numbers. Then what could the 4th quantum number possibly tell us if the first 3 specify any individual orbital? Well, the 4th one doesn't tell us about the orbital. As it turns out, the 4th one tells us about the electrons in the orbital. The three quantum numbers taken together will always specify a particular atomic orbital because they tell us all we need to know. How big it is, what it's shaped like, and its orientation in space. Now things get even weirder if we take hydrogen's electron and give it n equals 3. Now we have three shapes. We still have an s, except we call it a 3s because it's bigger. Meaning an electron in a 3s is going to spend more of its time further from the nucleus than in a 2s or a 1s. We also see p orbitals, but we don't call them 2p, we call them 3p. Still three of them, they're just bigger. We also see a new shape, and we call those d orbitals. Now, what does d stand for? Stands for diffuse, but you don't need to know that. What you do need to know is every time we find a new shape, there's always two more of them than of the previous shape. So there's one s, but there's three p's, and there's five d's. You don't have to know the name of the five d's, and you certainly don't have to draw them. All you need to know is that there's five of them. But if you wanted to diagram them, that's what they would look like, okay? Now, again, to the extent a flat page can represent three dimensions, notice that most of these have four lobes, unlike the P's that have two lobes. So we call this the VYZ because it's in the YZ plane. So if we call that the Z-axis and that the Y-axis, then that means those are right in the plane of the board. Okay? This one, the X is coming up. So those four lobes are in that plane. You see that? And notice that the lobes are between the axes, they're not right on the axis. So that's in the flat plane of the board, the Y, Z plane. Okay, so to the extent I'm able to do this, that plane is the plane of the board. Then we have one in the XZ plane. The Z axis is here, the X is coming up. So that one is in this plane with the lobes here, 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 and here. Okay. This one is the XY plane. That's this one. And again, the lobes are here, 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 and here. Not right on the axis, between them. So again, YZ, here, 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 and here. XZ, here, 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 and here. XY, here, 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 and here. Between the axes, right? And then we got one called a dx squared minus y squared. Same plane as this, except instead of being between the axes, they're right on them. So the axes go right through. Okay? Kind of goofy, right? And then this is a strange one. This is called the dz squared. It's right on the z-axis. And that kind of looks like a p orbital, but then we got this kind of goofy donut going around. And again, it's not a path. The electron doesn't do like a figure eight and then spin around that donut. This is just a probability volume. And you say, yeah, that's weird. It is. But those are the solutions to Schrodinger's equations. Will you have to draw them? God, no. Will you have to remember their names? No. All you have to remember is that there's five of them. And it's easy to remember because we go 1, 3, 5. 1s, 3 p's, 5 d's. We don't see d's until the third energy level. We don't see p's until the second. Fair enough? Yeah.
For the last shape, where did the two other balloon things go?
For which one?
For the last one, the one with
dz squared?
Yeah.
It's right on the z-axis. So it's the balloon, if you want, goes right through the z-axis, and then we got a donut wrapped around the middle of it. Oh. Yeah, it is straight. Notice that as n equals 3, there are three sublevels, three types of orbitals, three shapes. 3s, 3p, 3d. But now there's also a total of 9 orbitals, 3 squared. We've got 1, 3s, 3, 3p's, that's 4, and then 5, 3d's, that's 9, 3 squared. Now, what about 4? Well, this one gets interesting too. I didn't put the f orbitals, which is the next one, in the book because they're just too weird. But I'll show you the shapes. In the 4th energy level, we expect to see 4s, 4p, and 5 4ds. But we also see a new shape. And there's not 3 of them or 5 of them, there's 7 of them. Okay? And we don't see f orbitals until we get to the 4th energy level. Each higher energy level introduces not only another shape with a greater number by 2 of more complicated orbitals, but they're way more complicated. So remember that each p orbital had 2 lobes. Most of the d orbitals have 4 lobes. But the f orbitals look even weirder than that. And let's see if I can. Well, you guys can do this as easy as I can. And I was going to put it in the book, but then they said no, that would be too difficult for students to appreciate. Let's just go to images here. Let me find a good one. Maybe that's not bad. So there's the 7F orbital. You kind of get the idea, right? Pretty complicated. And one of the donuts shapes has 2 donuts. All right. And if you kind of look over here, this is, see if I can, maybe I can't focus on that. But that's when all the points of highest probability are connected. That's when we don't do it. But really, these little lights here are really where the electron density is the highest. All right. Now that's not the only set of diagrams you can find. There's a whole bunch. I've loaded this one before too. Okay. So there's a S, P, D, and there's the 7F. So will I ask you to draw those? No. All I need you to remember is there's 7. Okay. So let us go back. Yeah. There are 7F orbitals, each with a much more complicated shape than the d orbitals. You should remember the number of F orbitals, but that's really all. Okay. So we don't see them till the 4th, which kind of helps. F, and what does F stand for? Well, fundamental. So sharp, principal, diffuse, fundamental, SPDF. You don't need to know what the letters stand for. They're just names from wave mechanics. All you need to know is there's 7. So for the first energy level, the number of, or the n energy level, the number of shapes is n. In the first energy level, we got 1 shape. N equals 2, we got 2 shapes. That's n. Third level, we got 3 shapes, that's PMD. 4th, SPDF. The number of orbitals though is n squared. So in the first energy level, n squared is 1. All we have is an s. In the second, we've got 4 orbitals, n squared. We've got 1 2s, we got 3 2p's, that's 4. In the third energy level, we have 3 squared, 9 orbitals. 3 shapes, but 9 orbitals. 1 3s, 3 3Ps, and 5 3Ds. In the fourth energy level, we have 16. We have 7 4Fs. We've got 5 4Ds. We've got 3 4Ps, and we got 1 4S. And that's kind of summarized right here. Okay. Number of orbital shapes is N. And notice I said 4S sublevel, 4P sublevel. That's the shape. That's often the term we use. Number of orbitals, N squared. Okay. Now in hydrogen, if I take that electron and give it that amount of energy, at every energy level, all of the orbitals are at the same energy. So this is called an orbital diagram or energy level diagram. And notice that this says energy, not distance from the nucleus. It says energy. And you might think, well, it's the same thing. Not exactly. For hydrogen, it might as well be. But for multi-electron atoms, it isn't. Okay? So what does that mean? If I take hydrogen's 1 electron and I elevate it, I excite it to n equals 2. The probability of that electron being in any of these 4 orbitals is exactly the same, because they're all at the same energy. When I go to n equals 3, the probability of that electron being in any one of these 9 is the same. Or in n equals 4, any one of those 16. That is only true for hydrogen. It isn't true as soon as we get to a multi-electron atom. Okay? State what each of the 3 quantum numbers discussed so far tell us about atomic orbit. Well, the principal quantum number tells us the size of the orbit, the volume in the probability volume that it's occupied. The second quantum number tells us the shape, whether it's S, P, V, or X. And the third tells us the orientation of space. And you don't need to know the name of them other than that. If you don't need to know any of them in the magnetic metal. What is the difference between a 2px and a 2py? Well, they're the same size because they have the same principal quantum. They're the same shape because they have the same second quantum. The only difference is their orientation in space. 2px and a 2py are at right angles to each other. Okay, that's the only difference. Same size, same shape, just different orientation in space. What's the difference between a 1s and a 2s? Size. They're shaped the same. Another way of saying that is an electron in the 2s orbital is going to spend more of its time further from the nucleus than an electron in the 1s orbital. Although the shape of that probability volume is the same, it's just bigger in a 2s. Anytime we increase the principal quantum, that's telling us the electron, whatever orbital it's in, if it's got that number, that tells us the size of that, the outer edges, if you will, of that probability volume. Okay? And as it makes sense, as energy goes up, so should the size of the probability volume. Because it means that electron is going to spend more of its time from the nucleus. How many different orbitals are available to an excited hydrogen electron in the fourth energy level? 16. 16 different orbitals. And again, for hydrogen, if the electron is as likely to be any one of those 16 as any of them. Now, I wish it was that simple. And I wish it stayed that simple, but it doesn't. The orbitals of multi-electron atoms. Remember, the Bohr model worked perfectly for hydrogen, but it didn't work for multi-electron. Suggest the reason why that might be. Remember, Bohr saw the electron as a particle. But if it's a particle wave, what do waves do when we're in the same vicinity of space? Well, they cancel, they add, they interfere, right? Whether it's constructive or destructive, they always interfere with each other. Moreover, they got a negative charge. So we have negative particle waves interacting with each other in 3D space. And if electrons really do have a wave nature, then it would make perfect sense that when there's more than one electron around the nucleus, they're going to affect each other. And they do. Hydrogen is the simplest atom with one proton in the nucleus surrounded by one electron and one s orbital in its ground state. You didn't know what that meant 15 minutes ago, but you do now. There are no electron-electron interactions, either interference or repulsion. And in any excited state, that is, anything other than n equals 1, all of the atomic orbitals available to that single electron are of equal energy. Because there's no other electrons for that electron to worry about. It's the only one. We might expect a different situation, however, for multi-electron. Electrons are charged particle waves. It seems reasonable to conclude that they will affect each other when two or more of them occupy the same region of space around an atom's nucleus. And they do. To describe those electrons in multi-electron atoms, we must introduce several additional considerations, ones that we didn't need to worry about when we only had one electron. Experiments have shown that the single electron in hydrogen generates a tiny magnetic field. We believe that all magnetic fields originate from moving charges. The magnetic field in around every hydrogen atom, or any hydrogen atom, points in a direction that would suggest the electron is actually spinning on its axis, as if the electron were a spinning charge. You say, wait a minute, it's a particle wave. How can that be? I don't know. It's just that the magnetic field around any hydrogen atom is as if that charge was spinning. Also, in any sample of hydrogen, analyzing the many atoms present shows two opposing magnetic fields, which tells us that it looks like in half of the atoms, the electrons seem to spin one way, and in the remainder, they spin the other way. Now, you haven't ever heard this before, but as it turns out, an electron's spin is as fundamental a part of its nature as its charge. Now, what do these diagrams over here represent? In physics, there's a number of rules that come under the heading of what we call right-hand rules. One of them has to do with the direction of a magnetic field in a current-carrying wire, for instance. So let's say we have a coil wire like this. If you take your right hand and your fingers go in the direction of that current, your thumb generates the magnetic field. That's the right-hand rule. So let's imagine that the electron is spinning. If the electron spins counterclockwise, take your right hand, what's called the right-hand rule. Your fingers curl in the direction of the spin. Your thumb points up, right? That's the magnetic field generated in a hydrogen atom if that electron, as if it were spinning counterclockwise. Make sure you're using your right hand. If the electron spins counterclockwise, the magnetic field goes down, or clockwise, the magnetic field goes down, right? So counterclockwise, clockwise. That's the one in the bottom. Here the spin is clockwise. Notice the direction of the field is down. Now, that is the fourth quantum number. The fourth quantum number then is called the spin quantum number, m sub s. And you don't need to worry about the value being plus a half or minus a. It's either it spins this way or that way. And every hydrogen atom has a magnetic field in it. But in any sample of hydrogen gas, we don't detect the field, which effectively means that fields cancel. Half of the hydrogen atoms have electrons spinning one way, half of them have the electrons spinning the other way. Why? I have no idea. That's the way God made it. But electron spin is actually a foundation of magnetic resonance imaging. We take advantage of the spins on the hydrogen atom, okay, of the electrons in the hydrogen. You guys okay with this? Good. Are you going to need that in the test? No. But the arrow resulting from those spins, we are going to incorporate into a diagram, okay? So that's, now we've got 4 quantum numbers. The first tells us the size of the charge cloud, size of the orbital. Second, the shape. Third, the orientation and space. Fourth, tells us the spin of an electron in that orbit. Okay. We already know that we can identify any orbital in any atom by the use of the first 3 quantum numbers. But we must use all 4 of them to specify any electron in an atom. This is based on the fact that any atomic orbital can hold a maximum of 2 electrons, as it turns out. When 2 electrons are in the same orbital, they have the same first 3 quantum numbers, right? But if they're in the same orbital, there's no magnetic field we can detect, which means if they're in the same orbital, they got to spin in different directions. When 2 electrons are in the same orbital, their spins must be opposite. Originally proposed in 1935 by the Austrian physicist Wolfgang Pauli, this can be viewed as the first rule governing electrons in multi-electron atoms. The Pauli exclusion principle: no 2 electrons in the same atom can be described by the same set of 4 quantum numbers. The most they can have the same is 3. If they have the same first 3, they're in the same orbit. And then the 4th has to be different because they spin in opposite directions. So that's one way of saying it. Here's another way of saying it. If 2 electrons can occupy each orbital, the maximum number of this is another way to say this. If they're in the same orbital, they spin in different directions, or their spin quantum numbers are opposite. Okay. We noted earlier that the total number of orbitals existing in any level, n equals n squared. Well, if 2 electrons can fit in each orbital, then the maximum number of electrons in each energy level has to be 2n squared. N squared is the number of orbitals in an energy level, and 2 electrons fit in each one. So 2n squared is the number of electrons that can exist maximum in each energy level. A further consideration for multi-electron atoms is the effect of electron-electron repulsion on the relative energies of those sublevels. Remember, in hydrogen, there's only 1 electron, so there's no repulsion. But at any energy level, all the orbitals are the same energy. But not true in a multi-electron. For hydrogen, where no repulsive forces exist, all of the sublevels, all of the orbitals are at the same energy. And the chemist called it generate. This is not the case for atoms of other elements. We still have the same type of orbitals, so we still have the S and the P and the D and the F. It's just that they're not the same energy. Although the same types of orbitals exist in multi-electron atoms, their relative energies are different. Repulsive forces cause a sublevel with a greater number of orbitals to have a greater energy. So, for example, you would expect that if we've got 3 orbitals in the p sublevel, there's potentially more repulsion in there than an s, where we only got 1 orbital. So the p are always higher than the s in multi-electron atoms. In hydrogen, 2s, 2p. But in multi-electron atoms, 2s, 2p. And d orbitals have 5. So they're even higher, more repulsive force than the p. And f have 7. So based on the number of different orientations in space, S, there's less repulsive force than P, because I got 3 P's and only 1 S. P is less repulsive force than D, because there's 5 D's, but only 3 P's. And D is less repulsive forces than F, because F was 7. and D has 5. And remember that as we move up, the energies in each energy level get closer together, right? So what this means is sometimes we have overlaps. What's on the next page? Consider figure 5.6. Compare this energy diagram with a multi-electron or a multi-electron, any multi-electron out of hydrogen. Remember, in hydrogen, 2s, 2p. Third energy level, 3s, 3p, 3d. 4s, 4p, 4d, 4f. Not here. So, an s here. And again, this isn't distance from nucleus, this is energy. Okay? Distance from nucleus is the principal quantum, 100% of the time. But energy is not the same thing. So 1s is lower energy than the 2s. But 2s is lower energy than the 2p. And 2p is less energy than the 3s, which is less energy than the 3p. But notice how much further the 3d is above the 3p. So much so that the 4s is actually lower in energy. There's less repulsive force for electrons in the 4s orbital than there is for electrons in the 3d suborbital. Even though the 4 is outside the 3d, there's still less repulsion. Okay? Why does this matter? Well, when we populate electrons, we always start at the lowest energy orbital first. We fill them. So, look at these circles. How many electrons can I fit in an s orbital in total? How many can I fit in S? How many electrons go in each orbital? Yes? 2. How many electrons can I fit in a p sublevel? 6 in total. Say it.
6.
The sublevel, not the orbital. There's 3 of them. 6, right? How many can I fit in a d sublevel? 10, right? How many can I fit in the F?
13.
What's 7 times 2? What do you think? What do they say? This is the S block. This is the P block. 1, 2, 3, 4, 5, 6. This is the P block. Is the other block. That's why we separated them from the reason. Wherever the highest energy orbital we're filling in puts us. So we're going to use this now to describe atoms and electron in 2 ways. We're going to talk about a short form electron configuration, which is what's on there. And then we're going to talk about an orbital diagram, which looks like this. And you're asking yourself, how can I possibly remember that? It's easy. I'll show you a diagram. It's coming up. Let's not get ahead of ourselves. Electron configurations and orbital diagram. Imagine if you missed today's class. We are now in a position to organize electrons into orbitals for the atoms of the element, where they most probably are. Understanding this organization will prove to be a powerful tool as we discuss the periodic table and bonding in the next chapter. In beginning this process, we introduced the second rule associated with describing electrons and multi-electron atoms. The first was the alpha crystal, or the polyfusion crystal. Second one's alpha. There was no guy named Alpha. Alpha is just German for living up. So this just says when filling orbitals, when populating orbitals with electrons, the lowest energy orbitals available are always filled first. In other words, we start at lowest energy and move up. Not size, not distant from nucleus, energy. Okay. The order for filling orbitals is given above. in this diagram. So we fill the 1s, then the 2s, then the 2p, then the 3s, then the 3p. But we don't go to the 3d until we've started the 4s. After the 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f. And again, how are you going to remember that? Well, I'll show you. Using your ruler to do it easily. That's the diagram you guys are going to be able to generate, just not yet. Okay. I don't want to get too far ahead of ourselves just yet. So let's begin with hydrogen. And again, we're going to do it in its ground state. We're going to do the atoms in their ground state. So over here, I'll put the short form electron configuration. And then to the right of that, I'll sketch the energy or orbital diagram. Okay. And I'm not going to be drawing little circles. It'll be easier than that. So how many electrons does hydrogen have? One. Well, for hydrogen, the electron configuration, the short form is just written 1s1. That 1 is not an exponent. It's not to the power of 1. It's just read 1s1. We can use a shorthand notation called an electron configuration, which is written in the format NL number, showing the energy level N, the sublevel SPDRF, and the number of electrons respectively here. So that means in the first energy level, we have one electron in the 1s. Okay, 1s1. This tells us that hydrogen's one electron resides in a 1s orbital in its ground state. What about the orbital diagram? I'm going to draw that over here. Now, this x-axis really doesn't mean anything other, I guess, than zero energy. Okay, but it's important that what goes here is not distance from increase; it's energy. And at n equals 1, let's put 1 down here, all we have is a 1s. Now, in the diagram at the top of the page, there's circles. Let's use a line. Okay, that represents the 1s orbital. Okay. In other words, in the first energy level, that's all we have. We have a 1s. And we're going to indicate the electrons in the orbital by using an arrow facing either up or down, representing the magnetic field based on the spin. So, directly drawn, it's usually drawn like that. You guys see that little picture? Now, sometimes, just to save time, if you're lazy, they just do that. Okay. This tells us that electron in the 1s orbital, in this case, is spinning counterclockwise. Usually we start with the up arrow first. It doesn't really matter, but usually we start with the up arrow first. Okay. So that's the orbital diagram for hydrogen in its ground. When we go to helium, we have 2 electrons, right? Remember, any orbital holds 2 electrons. So helium is 1s2, not 1s squared, 1s2. And for the first time now, we got to put electrons in the same order. And according to the Pauli's exclusion principle, that electron must be spinning the other way. Okay. Now, in the first energy level, so the first energy level, that's all we have is an S. Okay. So by the time we got to helium, we're done the first energy. Okay. And that's what we do in the periodic table. At the end of every period, which is the horizontal rows, when we go down to the next, we always start a new energy. Okay. So when we get to lithium, And you now gotta go to n equals 2. Okay, so let's put n equals 2. Now, if this was hydrogen, we'd have 2s and 2p. But in a multi-electron atom, the 2s is lower than the 2p. So let's put the 2s here. Then we're gonna put the 3 2p's. And you don't have to call them 2px, 2py, 2pz. Just write 2p, okay? Lithium has 3 electrons. So 1s2, 2s1. And the number of these have to add to the total number of electrons. So where does that 2s go? Or that electron in 2s goes over. So we gotta find it. It hasn't been a fair yet. Yes, teachers are letting your kids on. But it's gonna be a prayer. I'm gonna keep going until there's a prayer. Make sense? 3 arrows, 1s2, 2s1. After lithium, we come to beryllium. You have 4 liquids, right? 1s2, 2s2. Yes. And look where we are in the periodic table. We've just finished those 2 tall ones on the left. After beryllium, we come to boron, right? Which is way over on the right. How many spaces are on the right? 6. Because for the first time, we start with 2p. Okay. So if we're in the p sublevel, we're on that block on the right. If we're in the s sublevel, we're on the block on the left. Think about it. Usually, should there be a prayer at the end of the block? There should be, yeah. Just that all the teachers have let their students out, and that wouldn't fall for their idea. They are, but you should still have that, right? Okay. Wow, guys, we've gone to choir. We'll take this up next. See if I can read to the end of the lecture. Right?